Welcome back to another video on design of experiments and analysis of variance. We've already covered hypothesis testing, which helps us make decisions based on data. For example, checking if a new material is stronger than an old one, or if assembly line A and assembly line B produce the same average number of defective parts per day. When we collect data from both lines, we get two datasets that can be visualized as normal distributions, or with box plots, and we use a t-test to determine whether the observed difference in means is statistically significant. But in the real world, we often need to compare more than two groups or test multiple factors at once. Imagine testing 3 different manufacturing processes to see which one results in the fewest defects. If we try to use multiple t-tests to compare every pair, we increase the risk of making type 1 errors, incorrectly concluding there's a difference when there isn't. To handle this, we use a single test called an F-test, which compares all group means simultaneously. This is where the F-distribution comes in, and where design of experiments and analysis of variance, or ANOVA in short, become essential. Design of experiments helps us plan experiments efficiently, allowing us to test multiple factors, like temperature, speed, or pressure, at the same time, rather than changing one at a time. This saves time and resources and helps you understand interactions between variables. ANOVA is the statistical tool that helps us analyze the results. It tells us whether the differences in group means are real or just due to random noise. Together, design of experiments and ANOVA form a powerful approach for solving complex engineering problems and making data-driven decisions in multivariable environments. An observational study is a type of statistical analysis where the researcher simply observes and records data without manipulating any variables. The purpose is to identify patterns, relationships, or trends as they naturally occur. However, because the researcher has no control over the conditions or influencing factors, it is difficult to determine whether one variable actually causes changes in another. In contrast, a designed experiment involves deliberately manipulating one or more variables, called factors or treatments, and assigning them to different groups in a controlled setting. This design allows researchers to isolate specific effects and assess whether changes in those variables directly cause a particular outcome. While observational studies are valuable for detecting associations, only well-designed experiments can provide strong evidence for causal relationships. A classic example that underscores this point is the observed correlation between ice cream sales and homicide rates. Data shows that both tend to increase during the summer months, but it would be misleading and absurd to conclude that eating ice cream causes violent crime. The actual explanation lies in a confounding variable: temperature. Warmer weather leads to increased outdoor activity, more social interaction, which can heighten tension, and higher ice cream consumption, all at the same time. This example highlights the fundamental principle that correlation does not imply causation. Without experimental control or further analysis, assuming a cause and effect relationship based on correlation alone can result in incorrect and even laughable conclusion. In observational studies, we just collect data as it happens. We don't control anything. The problem is, these studies are often affected by something called confounding variables. These are hidden or unaccounted for factors that can mess up the results or create false relationships between the variables we're measuring. Suppose we notice that ice cream sales and crime rates both go up in the summer. That doesn't mean ice cream causes crime. The real confounding variable here is hot weather, which influences both things. In contrast, experiments let us avoid this kind of confusion. We assign treatments, like different machine settings or materials, to groups randomly. This helps cancel out the effects of confounding variables and lets us study the true impact of what we're testing. We run experiments in engineering to address the following. 1. To figure out what causes changes in outcomes. For example, what causes a part to wear out faster or a product to fail? 2. To find the best conditions for performance, like what temperature and pressure settings produce the highest quality welds. 3. To compare results across different levels of a variable. For instance, testing a component at different stress levels or voltages. 4. To build a model that helps predict outcomes, so we can forecast performance without running a full test every time. Experiments are a natural and essential part of engineering and science. Whether you're testing new materials, improving a process, or tuning a machine, you'll often run experiments to figure out what works best. As we said earlier, if we're comparing just two methods or settings, we can use the hypothesis testing tools we've already learned, like the two-sample t-test, to decide if there's a meaningful difference. But what if we have more than two options to compare? Let's say you're testing 4 different types of fuel or 3 different temperatures in a welding process. Running a bunch of two-sample tests increases the chance of making wrong conclusions. This is where ANOVA comes in. ANOVA allows us to compare all the group means at once, using a single test. It tells us if at least one group is significantly different, without increasing the risk of error from multiple comparisons. Let's go over an intuitive example to see why performing a sequence of hypothesis tests will increase the error in our analysis. A manufacturer of paper used for making grocery bags is interested in improving the product's tensile strength. Product engineering believes that tensile strength is a function of the hardwood concentration in the pulp, and that the range of hardwood concentrations of practical interest is between 5 and 20%. A team of engineers responsible for the study decides to investigate 4 levels of hardwood concentration: 5%, 10%, 15%, and 20%. They decide to make up 6 test specimens at each concentration level by using a pilot plant. All 24 specimens are tested on a laboratory tensile tester in random order. The question we need to answer is whether any of these hardwood concentration percentages will lead to a significantly different tensile strength. We are testing 4 different concentrations: 5%, 10%, 15%, and 20%, and for each level, with 6 specimens, giving us 24 total data points. Now, let's take a look at the averages. 5% concentration has an average tensile strength of 10.00 over its 6 specimens. 10% has an average of 15.67, 15% has an average of 17.00, and 20% has an average of 21.17. There seems to be an increase in tensile strength as the hardwood concentration increases. So, let's just run a series of t-tests, where we test tensile interest of 5% wood concentration versus 10%, 10% versus 15%, and 15% versus 20%. When comparing two groups, like 5% versus 10% hardwood concentrations, we use a t-test to check if the difference in means is statistically significant. Each t-test has a 5% chance, alpha of 0.05, of making a mistake, a type 1 error, by saying there's a difference when there really isn't one. But here's the problem: if we perform multiple t-tests, like comparing 5% to 10%, 10% to 15%, and 15% to 20%, the chance of making at least one mistake increases. This is called inflating the family-wise error rate. In this case, even though each test is run at a 5% error level, the overall chance of making at least one false conclusion jumps to about 14.3%. That's almost triple the risk. This is why we need tools like ANOVA, which allow us to compare all groups at once with a single test, keeping the overall error rate controlled. In short, when we do more comparisons, we also risk more errors, unless we use the right statistical tools to account for that. Thank you for watching another video on design of experiments and analysis of variance. See you in the next one.